All right, so in this video, we're going to start our look at the next force in our force list, the force of friction. So writing this out, we've got force of friction, also known as the frictional force. It's commonly written both ways. Okay, broad description of what this force is and how to deal with it. Sorry about that. My board was acting a little weird. It is a resistive force between two surfaces sliding or trying to slide past one another. So here's a description of the force of friction. It's actually caused by things not being perfectly smooth when you zoom in down to the atomic level or getting close to that. Somewhere in that range, on the microscopic level anyway, you've got a bunch of bumps and little valleys and stuff for any two objects that would go together. And as those things try and slide past one another, they have to kind of scrape over one another. So that's kind of an explanation of where it comes from when you get down to the very small level. Normally, if things are rougher, they would end up with a little bit more friction, or if they're smoother, but nothing is perfectly smooth, and so if they're smoother, you would usually end up with a bit less friction, all things being equal. Okay. One of the things that makes friction a little bit difficult, and why it's probably going to be several lessons for us, this lesson and then probably a second one that'll be coming up, is that there are two types of friction. First is kinetic. Well, not necessarily first, but the one that we're going to look at first is kinetic. Now I'm going to emphasize this. This is when the two surfaces are sliding with respect to one another. And then there is static friction when they are not sliding, but trying to. I'm going to pause here for just a moment and point out that a common misconception that students have is they will fall into the habit of saying kinetic friction is when the objects are moving and static friction applies when they are not. While that's something that you're probably going to see as a fairly common thing to show up, it is not guaranteed, and many students will be caught off guard if they try and embrace that. So I really want to emphasize this. Do not fall into the common trap of thinking kinetic applies if things are moving and static applies if things are not moving. Kinetic friction applies when the surfaces are sliding, and static friction applies when the surfaces are not sliding but trying to slide. Now, that may seem like an odd distinction, but we'll see in some of our examples as we go through why that's an important one to embrace. All right, but we'll get back to that soon enough. On the AP exam and the regular equation sheet, it usually looks like this. Big F for force, little f for friction, is less than or equal to some weird looking character that's actually a Greek letter. It is the lowercase mu times the normal force. Now we're going to unpack that in just a minute and give a table or a listing of what each of those things are. But first off, I'm going to go ahead and give us a subset of this. Kinetic friction slightly modifies this equation. So I'm going to mark this as FF for force of friction and then with a little k for kinetic. For kinetic friction, this becomes an equality. In other words, it's a regular equation. That the force of kinetic friction will be equal to this weird Greek letter that we're going to talk about, but it's a number, times the normal force. Which normal force? Well, we're going to talk about that too. If you're working with static friction, however, that one is the one that we get the less than or equal to. So force of friction, static friction, is less than or equal to this strange thing except for static friction. We're going to have two different numbers, one for kinetic and one for static friction. Okay, though they are very, very similar. To save space, the AP exam in the generic form of the equation is that the force of friction is less than or equal to this times the normal force. And that is a true statement because for the force of kinetic friction, it is equal to that, not less than. And the force of static friction gets a little bit trickier. That's what we're going to see in the beginning of the next lesson. We're going through introducing the materials here and going to take a look at least one example problem for this lesson. And then we will take a look at a couple of example problems in the next lesson. Okay, so extending the page, filling in what we're taking a look at. So first off, we have FF, either with a K or an S if you would like to specify that, but often on my materials in the AP exam, we will simply identify it as just the force of friction, FF. You might have to intuit or figure out what type of friction is at work here. This is the magnitude technically, but it's the force of friction. So this is our numerical value for the force, how hard friction pushes or pulls. Okay, let's see. We've also got that weird Greek letter. Now the easiest way to draw this is actually to draw a lowercase u and then put a tail on the front. That's the easiest way to actually represent and draw this character if you're not familiar with Greek. Mu sub k or mu sub s is something called the coefficient of friction. Now for mu sub k, it would be identified as the coefficient of kinetic friction, and mu sub s, it would be identified as the coefficient of static friction, the two types of friction you might encounter. Fn, our normal force. This is the contact force between the surfaces. Now remember, friction's all about two surfaces that are either sliding past one another or trying to slide. So the normal force is actually how hard those surfaces are squeezed together or pushed together. In fact, that's my next line on here, is to describe, here's kind of the technical, the contact force between the surfaces. Here's how you can understand it. How hard the surfaces are pushed together. Now, we will often see that this is the normal force that we usually apply, say, in a free body diagram, that is, at least in part or in whole, fighting against the force of gravity, the thing holding it up. That's if you've got something on flat level ground. We'll expand on that as we go, and again, you can apply Newton's second law, draw a free body diagram, and then work through that to see what the actual relationships fully are. But it isn't always from the ground. So for instance, we can take friction. I'd recommend doing this. Take your hands and put them together, and then rub your hands back and forth. Now there's a little bit of resistance. It's kind of difficult to move your hands back and forth, but not really at all actually, not much resistance. That is kind of the regular force of kinetic friction. We know it's kinetic because my hands are sliding with respect to each other, not necessarily because they're moving. Okay, on this, now let's increase our normal force, because our equation basically says that the force of friction depends on the normal force. Bigger normal force can allow for a bigger force of friction. And in kinetic friction, bigger normal force will result in a bigger force of kinetic friction. Okay, so take your hands and really push them together. And now try sliding back and forth. You'll notice that it is much harder to slide back and forth because as we increase how hard our surfaces are pushed together, the normal force, we also increase the force of friction. Okay, let's take that to the other extreme. So I'm going to take my hands and I'm going to put them together like this. They're not actually together, but the normal force between these two, how hard are they pushed together? Well, they're not pushed together at all, and therefore my normal force is 0, and I end up with no, at least frictional force from my hands, no frictional force between my hands. Now, there is some reaction to air, but we're mostly ignoring that. Okay, so that's a breakdown of how the normal force comes into play, and in general, you're usually looking for, when things are on flat level ground, it's the normal force pushing up from the ground into the object is usually the thing that's going to cause most friction, but not all friction. So we could also have something where I push up against the wall and I push hard enough to actually hold it. Or I'm holding up some papers here with a magnet. The magnet is actually squeezing the papers up against the whiteboard, and there's enough friction to hold it. If I put too many papers here, then it will slide down. Not that the magnet is any weaker, but because we've now overcome how much friction there can be. We'll see that a little bit more with the static friction in the next lesson. Okay. Now we need to talk about the other part that we see here. First off, I'm going to talk briefly about the units to make certain that we finish up our list here. Force of friction, like many of our forces, our preferred unit for that is newtons. I'm going to skip over this new weird thing and come back to it in just a moment. But we've got normal force, which is also in newtons. Okay, I've got a little bit more that we're going to add into this. You don't necessarily need to write this next part down, but I want you to kind of see it because it's something that's important to understand as you move into physics. We're going to end up deriving a lot of expressions, different equations, and you're going to end up with things like acceleration equals some stuff, that sort of thing. We found a number of examples where we've done that sort of thing throughout AP Physics, so that's something that we need to be prepared for. One of the things that I want to emphasize, we're getting to the point where the equations are going to become more complex, and one of the things that you can do to double check that the equation could be correct, or alternatively, can check whether or not you know that it is incorrect, is that the units on one side of an equation must equal the units on another side of the equation. So for instance, let's take one of our classic kinematic equations. We've got delta x equals v naught times time plus 1/2 at squared. Let's think about the units. I've got delta x would be measured in meters, and I'm saying that that needs to be equal to, well, a velocity would be in meters per second, and I'm multiplying that by a time, that would be in seconds. We can see the seconds cancel out, and this term actually has units of just meters with these two combined. Plus 1/2, well, that's just a number, doesn't have any units. Acceleration has units of meters per second squared, and I'm going to multiply that by a time squared, where that's seconds, and then I'd square them, and then the seconds squared cancel out, and I see that meters would equal meters plus meters. Well, all of my units work out. For an equation to be possible, the units absolutely must work out. So when you're deriving an expression, if you get to the end and you have some time, you might double check that your units work. If your units don't, you can be guaranteed it is not the correct answer. You might go back and maybe you can track down where you made a mistake. The reason that I bring this up is we're now looking at a force of friction equals the coefficient of friction, this thing that I've introduced but I've not talked much about, times a normal force. Well, the units have to work out. Newtons is on this side with this force equals question mark times newtons. Well, in this case, I could solve for it by dividing both sides by newtons, and I end up with no units. And that's one of the things that I want to emphasize on this, going back to our actual page. I'm going to scroll down to it. I put the units in here. This is one of the first times, but not the only time, that we're going to encounter a value that has no units. Now, I've made a big deal that numbers in the past, that numbers are pretty much meaningless unless they have units. But this is something that you're going to see a bit more if you go into science and engineering in particular. Engineers and scientists really like having what's called dimensionless units. They're usually set up by making a ratio of something, but in this case, we've got no units on the coefficient of friction. And one of the beautiful things about this, one of the reasons engineers and scientists love these quite a bit, is it doesn't matter if you're using newtons or pounds, whether you're using meters or feet, because this is set up as a ratio of some kind and the units cancel out, we will actually have the exact same value no matter what unit system you're using. And that's really powerful, especially in engineering, where you might be using different units depending on where you're working and what field in which you work. Some examples of this. You may have heard of it before in aerospace engineering. They have something called the Mach number. Now, the Mach number is taking your speed and dividing it by the speed of sound, so the units cancel out. So it doesn't matter if you've got miles per hour divided by miles per hour gives you no units, or if you have meters per second divided by meters per second, you end up with no units. And you end up with the same proportion despite different unit systems. So we end up with what's called a Mach number. So if you're going exactly the speed of sound, you would take your speed divided by the speed of sound, but if you're going the speed of sound, that would just be 1. Mach 1 means you are going the speed of sound. Mach 2 means you're going twice the speed of sound. So if we're working with meters per second, that would be, for Mach 1, that'd be about 340 meters per second. And if we were working with miles per hour, that would be about 760 miles per hour. So for anyone using whatever units they're comfortable with, that one number with no units actually gives them a lot of information. There are a bunch of other units or things that you will study if you go into science and engineering that have no units by design to make them a little bit more functional. In this case, the coefficient of friction is one of those things. Okay, now that we've talked a bit about that, let's finish this up. Let's talk about the coefficient of friction itself. So there are a couple things that affect friction. One, like we already talked about, is how hard you push the surfaces together. But one of the others is what I like to describe as the roughness. So for instance, I've got some friction here. If I put some water, I've got a sink right over there, if I put some water on my hands, they might slide a little bit easier. Or if I covered them in, say, some oil or something slick, they would actually slide much easier. Even if I squish them together, it would probably still be a lot easier because I'm changing some of the surface properties. And since that's an important part of friction, that's actually what the coefficient of friction describes. So now we're going to look closer at the coefficient of friction. This thing describes, for our purposes, the roughness of the surface. Now you might be tempted to say the smoothness. They both kind of say the same thing, but in this case, I say the roughness because bigger number would mean more rough, and that corresponds to how mu operates. Big number means you've got more friction overall. If you were to say that this describes the smoothness of a surface, then a big number would imply a lower friction. And so in this case, I usually describe this as the roughness. Now that's not exactly what this is, but it's a great way to think about the coefficient of friction. Now, this is the roughness, I'm going to emphasize this, between the two surfaces. So it's not just something that you can get from one surface. You'd always have it where it's like rubber and concrete, or we could have wood and concrete. But the only way that we can talk about the coefficient of friction is by knowing both of the surfaces together. Because some of them might go really well together and some of them might not go really well together. It all depends on both surfaces. So even with needing both surfaces, I've found that it's usually easiest to think about the coefficient of friction as representing how rough the surface is. Okay, the regular range for coefficient of friction is usually less than or equal to, greater than or equal to 0, and here's mu, and it's usually less than or equal to 1. So if you have something that's super slick, like something on ice, ice might have a coefficient of friction that's close to maybe 0.1. Might be nice and slick. If you have something that's really rough, or has a lot of friction based on its surface, like sandpaper, you might have a value more like 0.9. Now the last thing that I'm going to say in this before we switch over and take a look at an example problem is you can actually have coefficients of friction greater than 1. It's not like 1 is a magical barrier on it, but most likely you're not going to see those very often. You might see them in some of our labs, but we usually don't write questions about things that go over a value of 1 for the coefficient of friction. And I'm going to talk briefly about why that is. 1 is kind of where what we're describing, the surfaces sliding past one another, maxes out around 1. Now you can have stuff that acts like that is a bit above 1 or noticeably above 1. The example I like to give is this. My shoes have pretty good friction with the ground so that I don't slip and slide all over the place. Granted, the ground's not made of ice or anything like that. Maybe my mileage would change if it's ice or if it got wet from rain or something like that. But one of the things that I will compare that to is if you go to a movie theater, you might have extra, well, it's not actually friction. It may be harder to walk. You might end up with more trouble there. But in that case, if someone has spilled a soda and it's gotten dry and sticky, there's a difference between sticky and friction. And there are some things that start to act a little more sticky, and they would definitely be above a coefficient of 1. So a lot of times what we found is as you get about 1 or higher, you're not dealing with just pure friction anymore. You might be dealing with another effect. The most common ones are if it's a little sticky, that's a common one, or You may also notice noticeably higher than 1 on if you have some really soft foam, like on a bed or something like that. You put something heavy and it sinks down into the material and kind of makes a little divot, a little push down hole that it's stuck in. So for you to drag it, you're not sliding it just across the bed. You have to kind of pull it up over the bump and then kind of squish part of it as you go. And that makes it where you end up with effectively more resistance, but it's not really what friction is trying to embody. So in general, most likely your values are going to be between 0 and 1, and by the time you get to about a value of 1 and above, you're starting to move out of what we would call friction and into another type of force, some other resistive force, like I said, gluing something down, sticking. Okay, so this is a breakdown of the types of friction, at least initially, and some of the basic information that we need. We'll be back in just a minute to take a look at an example. All right, so picking up where we left off, we're going to jump straight into example number 1. Now, this example is based around a real live problem of, we're going to call this fall cleaning, or autumn cleaning if you prefer. So fall cleaning, and I'm going to need to do some deep cleaning in my house. So we need to, on a regular basis, we'll usually go through and sweep the floor and mop it up in all the common areas, that sort of thing, to keep things nice and clean at home. We have several cats, so if we don't do that on a semi-regular basis, we will be overcome by all of the fur and the love. But we usually clean that up on a regular basis, but there are places that are a little bit harder to reach. Say, underneath furniture, like under a couch, or a love seat, or a recliner, or something like that. A common one that we would need to take a look at in the kitchen is moving the fridge. So here's my plan. I need to move a fridge out of the way. Here's my refrigerator, and then here's me. I need to push on this fridge and move it out of the way so that we can get it out of its actual little cubby, and then we can sweep in there, we can mop, we can kind of treat the floor. Now, it might be that I need to get this entirely out of the kitchen, although honestly with the numbers that I have, because I'm about to give you some numbers, they're not realistic numbers for a full-size fridge. They might be more akin to a mini fridge. So in this case, I have a mini fridge in my classroom. Don't tell the administrators. But it helps keep some of my science stuff cold, although I mostly use it for my lunch. But it might be a better representation for these numbers if I were to identify it as a mini fridge. For our purposes, we're going to go with the numbers that I've got, though. I'm going to say that the mass of that fridge is 60 kilograms. Now, you can assume that I've unplugged it and that I've actually moved everything out of it. And here's what I'm going to do. I'm going to say that I am pushing this at a constant speed of 0.5 meters per second. It's about 1 foot per second. Okay, I'm going to stop here for just a moment. That may seem a little weird. This is one of the first times that we're encountering phrasings like this, but we're going to see why it's important in physics that we actually include some of this information. But I also want to say that this isn't just us going robotically, here is what I am doing, so that you have a full description of absolutely everything. What we're actually trying to describe is, this is how regular people push stuff. So if I were pushing something, I'm going to push, get it moving, and kind of go at a constant but comfortable rate. So if I've got something really big, or I'm a little worried about controlling it, I might go fairly slowly, but at a constant rate. Or if I'm in more of a hurry, I might go at a fast rate, but still usually at a constant rate. Most of the time people aren't speeding up actively or slowing down, at least for a large portion of their pushing. They'll have to speed up at the beginning to get the thing moving, and they'll have to slow down at the end to stop moving. But usually in between, most people will pretty quickly get to a comfortable speed and push at that rate. So when you see this, it's going to say pushing at a constant velocity or pushing at a constant speed. It may sound very robotic, but remember, what we're actually doing is we're telling you, hey, we're pushing it like a regular person would normally push it. Now, there might be situations where you wouldn't necessarily push it like that. If a car were screaming towards you, that would be terrible, and there's a baby carriage there, you might push it very, very quickly and try and speed up as much as you can to get out of the way. So there might be examples where we wouldn't necessarily push at a constant speed. And that's why we have to say this is what we're doing, because there's the possibility that we might not be doing that. And we're going to default, it doesn't look as good on the AP exam or standardized testing to say we're pushing this like a normal person, because that's exclusionary. Maybe some people push their own way in a dance form. This is a technical way of us getting across important information, and it's mostly just a way of covering our bases and saying, hey, we're pushing it like people regularly push, unless they have a strong reason otherwise. Okay, that's a lot of talking on that, but it always bugged me going through physics where it's like, why do we have these phrases in there? Well, you're going to see why we need to actually cover our bases on that, but I also want to express we're being technical and describing the details that are pertinent to our problem. Okay, so here's what I got. Roundabout way, we're going to explore this new idea of the coefficient of friction. So here's what I want from you all. I want us to find the coefficient of friction between the bottom of my fridge and the kitchen floor with me pushing it. Now I'm going to bring in some additional information. I'm the one pushing it, and I feel that I am pushing it with a force. It's about 130 newtons. It's about 30, maybe 40 pounds or so. And so I'm pushing it a decent amount, but I'm not, getting super tired moving this around. It's a lighter weight fridge, like I said. So that is some information that I will give you. I know, because I'm the one pushing on it, that I'm pushing with about 130 newtons worth of force. That's about 30 pounds or so. And again, we could pick up a bathroom scale, and then I can push against the wall, and we could see, it's about this. It's a decent amount. Probably not enough to move a full-size fridge, but enough to get the mini fridge sliding. Okay, so this is the information that I've got, and I believe that's all the information that you're going to be provided for this problem. But our goal is, we want to try and understand a little bit about this new idea, this coefficient of friction. We've dealt with some forces before, we've dealt with some motion before, so this is the thing that's really new. Okay, the first thing that I'm going to ask is this. We've got two types of coefficients of friction, because we got two types of friction. There's kinetic, and then there's static. Which one are we looking for in this problem? Well, I said that I'm already moving, so you might be tempted to say, oh, we're moving, and therefore it is kinetic friction, but I'm going to remind you, be careful assuming that. In this case, what you really need to ask yourself is, are you sliding? Is the object in question sliding? And my refrigerator is in fact sliding. So this is a case where, whichever approach you use, you'll come to the correct conclusion that we are dealing with the coefficient of kinetic friction. Okay. In this case, let's talk about problem solving. Now, we've gone through and looked at kinematics, and that was the first main unit that we looked at. And we had a nice orderly kinematic equation sheet that could tell us exactly what equation to use. Well, unfortunately, as we move forward in physics, we won't have anything quite that nice and straightforward, so we've got to start developing these skills without having it laid out in a grid form that you can just go along and find the correct equation. But all the same ideas are still there. Step one, identify what you're after. We're after the coefficient of kinetic friction. Okay? Step two would then be, do we know any equations that have that value in it, that variable? In this case, this is one of the nice things, we literally have only one equation. It's the force of friction is equal to mu sub k times our normal force. Now you may say, Sanchez, wasn't it less than or equal to? Well, that's if we were using static friction. Since we know we're looking at kinetic friction, I can go straight to setting them equal. This is the one equation that has the coefficient of kinetic friction in it. So, we know which equation we're going to have to use. In order for us to get this value, it means that to solve for it, we need to know our normal force and we need to know our force of friction. Okay, well, that provides some problems because one, force of friction, I only have one equation for that, and it's this equation, so I can't use that equation on two unknowns. I won't be able to solve for them. And on top of that, the normal force doesn't even have an equation at all. Oh, but wait. I was given a normal force. I wonder if that's the one in the problem. Is that how hard the surfaces are squished together? Am I pushing the fridge against the... Oh, no, I guess I'm not. I'm pushing to the side. That's a different force than what's squeezing the surfaces together. Well, It's easy to get overwhelmed on this, especially if you've identified the correct equation. Great. Don't lose track of what we need to do. Again, it's going to be a little bit more complex than kinematics, but let's think about this. Okay, let's set aside force of friction for now. Let's go with a normal force. Normal force we've solved before. We've got some experience. Either it's given to us. Well, we were given a normal force, but it's not the actual force that's pushing the two surfaces together. That's a common mistake students might make. And if we weren't given the normal force, our other option is to apply Newton's second law. In fact, when you're working with this, it's probably a pretty safe bet if you're looking at forces that at some point you should probably draw a free body diagram. So I'm going to draw my free body diagram. I'm going to go through my force list. We're partway through learning all of it. So starting at the top, we got force of gravity. There is a force of gravity on the fridge. I'm going to go straight to marking it as the mass of the fridge times the acceleration due to gravity. You can continue to mark it as Fg, but in this case, this is such a common replacement because that's the equation for the force of gravity that's actually usually what's listed on the AP grading rubrics and what we usually expect students to write. Now, you still get credit with Fg because that's a perfectly good way of representing the force of gravity. But we have a force of gravity on the fridge downward. And I'm drawing the free body diagram of the fridge because I'm looking for an effect of its friction interacting with the ground. Okay, normal forces. Well, we have a normal force holding this up, and that's the one that we, no pun intended, normally mark as F sub n. That is also, as we described earlier, how hard the ground is pushing up on the fridge. In other words, how hard these two surfaces are being squished together. Okay, great. So this is the normal force that goes in here. But we're not done with our forces yet. While you might be tempted to stop there, remember Newton's second law says motion and changes in motion happen because of all the forces acting on an object, not just one or two. Okay, so let's keep going. There is another normal force I am pushing, I'm going to, according to my drawing, to the right with a force applied to the right. It also has a magnitude of 130 newtons, but I'm going to leave it marked as Fa for now. Okay, those are the only things touching the fridge, so we're done with normal force. Moving forward, we have force of friction, and for the first time in our example problems, we do have a force of friction. Now here is where we can ask the following question. Friction opposes sliding, or it would oppose the sliding that would happen. So basically, friction is a resistive force. It opposes sliding, and I really want to emphasize that. Notice how I'm using that word sliding and not motion, because those are not necessarily the same thing. In this case, the fridge is sliding to the right, so our force of friction is going to oppose that and point back to the left. So I'm going to mark this as force of friction. You could also mark it as FFK if you would like, but we start to end up with a bunch of subscripts. It can be a little bit of a pain. Okay, so that's our force of friction. Next up, force of tension. We haven't studied that one yet, but we do know that it would be based around ropes and wires. I don't have any of those on my fridge. Air resistance, drag force. We don't have to worry about that unless we're told to include it. On top of that, I'm not pushing the fridge fast enough for air resistance to be a big issue. And finally, force of thrust. Do I have any rocket engines attached to my fridge? Well, no. But no. Okay. Oh, look. The force of friction also shows up over here with my free body diagram. That was one of the things that I said I didn't know how to find. I might have a clue as to how to do that. Okay, but let's start with the normal force. We said that that's what we were going to look at. We want to apply Newton's second law, which is the sum of forces equals our mass times our acceleration. But we have to break this up into the x direction. The sum of forces in the x is equal to the mass times the acceleration in the x. And in the y direction, sum of forces in the y is equal to our mass times our acceleration in the y. Okay, I'm going to go through this a little bit faster. We've got some practice with this, and the more practice you get, the faster it goes, which will be very important by the time we get to my test or the AP exam. You need to be able to do this, not only do this, but you need to be comfortable enough with it that you can do it relatively quickly. So I'm going to go with the y direction here. I have the following. I have a normal force up, so that's positive, minus the force of gravity, which is equal to the mass of the fridge times the acceleration due to gravity. Those are my only two forces in the y, so I'm going to set that equal to the mass of the fridge times the acceleration in the y direction. Okay, Now, we've got a bunch of stuff that we can fill in. We've got masses, and we know the acceleration due to gravity. But I have to ask you, what is our acceleration in the y direction for our fridge? Now, if your mind immediately went to negative 9.81 meters per second squared, that's one of the things that we need to address as we go into this section. You have to actually think about what the motion of your object is. Remember, forces cause motion, cause changes in motion is more technically correct. In this case, if the acceleration in the y were negative 9.81 meters per second squared, it would mean that my fridge is falling, but my fridge isn't falling. In fact, it's staying completely level, and therefore it's not jumping up off the ground, and it's not sinking down into the ground, so my acceleration in the y direction for this problem is 0. This value is 0. So I'm going to plug some things in. We've got our normal force minus the mass of the fridge, which is 60 kilograms, times our acceleration due to gravity, which is technically 9.81, positive, because it's g, not negative. But we're going to use the AP standard of using 10 meters per second squared. We're going to be slightly off the real value, but it'll keep us moving for this particular lesson, and many of our lessons for that matter. I've got 60 kilograms times 0 meters per second squared. This comes up to 0, and technically the units become newtons. In fact, we would have newtons minus newtons equals newtons. Our units must work out. Okay, so we end up with Fn minus 600 newtons is equal to 0. And we can then find that our normal force is equal to 600 newtons. Okay, so that was one of the things I needed. I'm now going to apply my sum of forces in the x direction and see what I can find out. So we've got my force applied to the right minus the force of kinetic friction to the left, and those are the only forces, so that would be equal to 60 kilograms times my acceleration in the x. Well, what's my acceleration in the x while I'm pushing it across my kitchen floor? Now you might be tempted to say, oh, it was 0.5, but let's wait. Pay close attention. I'm pushing this at a constant speed of 0.5 meters per second. Those units tell me that that's the speed at which we're moving. And I say that it's a constant speed. So what's my acceleration in the x while I'm pushing the fridge across the kitchen? Well, because it's a constant speed, I'm neither speeding up nor slowing down. My velocity is staying constant, and therefore my acceleration is 0. So this is another example where we have to pay close attention. Don't assume because we give you a number that you inherently must use that number. Sometimes we have additional numbers in there. And I've had students and parents complain before where they say, well, you're just trying to trick us. We're in the modern age. You can pull out your phone, ask a question, and you get way more information than you could possibly ever need or want to use. So one of the most important skills that we need is for you all to develop thinking that says just because something is there doesn't mean that I have to use it. We'll see. We got to see how to use the tools to understand. Oh, and this is 130 newtons minus the force of friction equals 0 newtons. So I can add the force of friction over, and in this case we will find that the force of friction has a magnitude of 130 newtons. Now notice, technically it would be to the left, and you may be tempted to put a negative there, but the negative was here to keep track of it, and we've added it over, and therefore we are finding just the magnitude of that force of friction. Okay, great. Going back to our original equation, we are almost done. The force of friction is equal to the coefficient of kinetic friction times our normal force. Okay, well I can replace this. I now know that this is 130 newtons equals mu sub k times 600 newtons. I divide both sides by 600 newtons, and I get mu sub k will be equal to 130 newtons divided by 600 newtons. And as we mentioned before, the newtons cancel out. If you were keeping track of this in pounds, then the pounds would cancel out, and we would still get the exact same number. Okay, here we go. 130 divided by 600 gives me approximately a coefficient of friction of 0.217 with no units. While you may be tempted to try and put some units on there, there aren't units for this particular value. Okay, that actually makes some sense. While it would be difficult to push the fridge across the floor, mainly because it's so heavy, for want of a better term, usually a kitchen floor is going to be fairly smooth and easier on average to get things across. Now, if I were to push this into the adjacent room where there's carpet, it would probably be much harder for me to get the fridge to slide across that carpet. especially depending on what type of carpet it is. Okay, but here's where we go through and apply one example, applying the concepts of friction and getting an understanding of our coefficient of kinetic friction. All right, until next time.